Hello, 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 CheersKevin here, and welcome back to some more Kerbal Space Program where we are working on our KOS script. And I think I finally have something that's working. I apologize for some of the delay in getting us here. Last week was unfortunately feeling very, very sick. Family was sick as well, which meant kind of available time for making videos. This is a little tricky, but we fixed some bugs in the last video, and we're now ready to get working on our transfer to the moon. Now, in theory, we've been working on this for a while. I'm excited to say that we're going to close it up in this episode, come hell or high water. Okay, so real quick, I want to go over our strategy. So there's a bit of a challenge in doing this, and this is actually, I do want to set this as the target just to kind of walk through. Here's a bit of the challenge, and that is, well, we don't get from KOS this closest approach value. And our idea of optimizing a maneuver is, hey, we need to give it some sort of score that it can improve upon. So if we were to try and say, hey, we want to figure out what the distance is at closest approach and say, hey, that's bad because it's a high distance, you know, assuming that it's, I don't know, vaguely here is the closest we get to the moon, then that is a worse orbit than this orbit. This orbit would be better. And so we can make incremental improvements to our maneuver node and it can find a wonderful maneuver. But the problem is we don't get this closest approach value. There's no way that we can access this through KOS. We can try and search for the closest approach, but thanks to El Wanderer I encountered a little note that even KSP sometimes has trouble finding this, and there's a reason for that, is that the closest approach when you have a body like this is not necessarily in one place. It's not that you get closer and closer and then you get farther away. Sometimes you get closer and then maybe you go farther and then you get a little closer again. If we pass the orbit, you can see how that might occur, right? So we go here, you know, we're getting closer, closer, closer. We get a little bit farther, then we're closer again, and then we get far away. So when we're trying to calculate where that closest approach is, it's hard to make sure that we're remaining consistent. And part of the reason that I've been encountering issues trying to get our hill climbing thing working is that it relies on us being able to give it a definitive answer, and it expects the problem that we're solving to be something that's it's called a convex problem, something where the answer is continuous. So, okay, jargon out of the way, what do we do then? If we don't know what our closest approach is, and even if we try and calculate it, there are sometimes, you know, multiple, I mean, theoretically, there are two peaks, but one of them is the closest peak. Whatever. So what are we going to do instead? Well, how about we just assume, when we're calculating this, that whatever we're looking at, we're just going to calculate the distance to the moon when we're at the apoapsis of our orbit. And we'll say, maybe the closest approach to the moon is actually when we're here, but whatever, we don't care. We're just going to calculate. We're going to say optimize so that the apoapsis, when we're at apoapsis, our distance to the moon is as low as possible. And there are kind of two conditions that we have to consider here. If we have an orbit that is like this, well, then we have no apoapsis. So here we can substitute the periapsis of our Munar encounter to figure out our distance from the moon. So we'll say, hey, if you have a transfer, then great, your total distance from the moon is blah. If we don't have a transfer, then your distance from the moon is whatever the distance is at apoapsis. So that should give this a way to sort of make that progress, because our distance at apoapsis here is bad, our distance at apoapsis is a little bit better still, and now it gets even better. And not only that, it presumably will now have some incentive to start wiggling our periapsis closer and closer, which is what I ultimately want. Because once we get on a collision course, then we can just turn around and suicide burn and everything should be hunky-dory, right? Okay, so that's the strategy that we're going to be following. But there's another wrinkle, and that is that because of the way the maneuver node stuff works and the orbit stuff works, we don't actually know when this apoapsis is, so we can't really figure out our position at that time. We need to actually solve for our apoapsis time, and that can be tricky as well. So we're going to dive into some code. We're going to look at that. We're going to use a different strategy to kind of figure out where the highest part of our orbit is, presuming that we execute the maneuver node, and then given that time, we can then compute the distance between the two objects. So we can say, hey, what is the moon's position at that time, what is our position at that time, and what is that distance. And we can use that final result to give our maneuver node a score and then let it go ahead and incrementally improve itself. So, a lot of words there. Let's dive right in. All right, so we have do transfer, and let's go ahead and uncomment this. I apologize if this is not as uncommented as it was before. We did add a protect from past function, which we can use to to enhance this moon transfer score thing. The idea is, okay, we give it an example maneuver, say, hey, how about 30 seconds from now with 0 delta V in any direction? Is that a good maneuver? Yes or no? And then we say, go ahead, try and improve it based on this criteria. And protect from past to make sure that we don't evaluate any maneuvers that take place in the past, because those aren't particularly useful to us. And then finally, once we found that, we execute the maneuver. So we need to write this moon transfer score function. And we're going to model it off of this eccentricity score function, but it's going to be a little bit different. So moon transfer score, this takes in some data. It's going to get this list that we started with, or the better ones that it finds when it's trying to make yet further improvements. And we'll say, okay, so let's create a maneuver node based off of that data. And for our eccentricity score, we were only optimizing on some values, not all of them. But for our case, we're going to be letting it go ahead and tweak all 4 variables. We'll add the maneuver to the flight plan. We'll say local result is something. Remove the maneuver from the flight plan. Let's make sure we're copying there. And then return the result. So this is the thing we have to solve. Now, I talked through this a little bit when we were looking at our orbit. What we're trying to find is the maneuver that gives us the closest distance to the center of the moon. So there were 2 different conditions that we had to evaluate. We needed to say, if we transfer to the moon, then we can just return, say, the result to the periapsis of the next part of our orbit. We'll convert that into code soon. Otherwise, I'm going to set the result to what? We want to set it to the distance to moon at Apoapsis. And assuming some maneuver. So, of course, I write in English sometimes, I write in pseudocode sometimes, whatever. Now, I'm using set, so we're overwriting a result. Let's go ahead and just say local result is 0 here. And periapsis of the next part of our orbit we can actually get from the maneuver itself. So we can say set result to MNV orbit. So that's a suffix off of the maneuver, and this is the orbit that we get following executing the maneuver. And we can say next patch. And then we can just say periapsis. Now, the way that we check if we transfer to the moon is by just seeing if this next patch exists, because when we saw kind of in the game, when it colors the orbit, the parts of the orbit in different colors, that's what the patch is. It's an orbital patch, and if it exists, then we know that we've transferred. If it doesn't exist, well, then there's no reason for us to look at a periapsis of around the moon. So if maneuver orbit has next patch, then set the result to the periapsis of the next patch. Otherwise, set it to distance to the moon at Apoapsis. And that is that done. Except we've assumed this thing exists. So we've got to write that. Function. Distance to moon at Apoapsis. And this takes in a maneuver. And then we've got to figure out, hey, what is the distance? Well, let's assume we have local Apoapsis time is 0. I'm just going to set it to 0 for now, and we'll have to figure out when that happens to be. What we'll then say is, let's return. Now, what we need to do is we need to get the position vector of the moon and the position vector of our ship. We can get that by using position at, and this will give a ship at a time, so Apoapsis time. And this gives us some universal XYZ coordinate stuff in a vector. We don't care. We're going to subtract the 2 and take the magnitude of that to get our total distance. Go ahead and subtract position at moon apoapsis time and get the magnitude of that. And that is the distance to the moon at our apoapsis. But we need to find this apoapsis time. And that's going to be tricky. Our altitude above Kerbin is going to increase, and then it's going to decrease. So, it's an arc. And we need to find the highest point of that arc. We need to climb a hill. Well, we already have a hill climbing algorithm, right? We already have our improved converge function. So in theory, we should be able to reuse that, right? So let me mock that up. So let's say local apoapsis time is improved converge. And what does improved converge need? Improved converge needs a list and then some criteria to evaluate whether that's a better thing or not. So we'll say list and we'll say time seconds. Well, yeah, time seconds plus ETA, maneuver ETA. So starting at right now plus however long it is until the maneuver starts, try and optimize by taking steps in a direction to get us a better altitude. So let's say highest altitude. Rather than actually write the function out, because I know we're going to end up getting rid of it, but I just want to walk through this. We need a period here. We'll just write this in line. I'll say parameter. This is going to give us this data, and I'm going to say, okay, how do we calculate our altitude at a particular time? Well, we can do the same trick of just measuring the position of the ship relative to the position of something else, in this case, Kerbin. And we'll say position at, so we'll say return, let's say local t. So the time is data 0. We'll say return position at ship apoapsis time, or ship t, minus position at Kerbin at t magnitude. And of course, since our improved converge is trying to get a small value, not a big value, we want to return the negative of this because we're returning the improved converge expects us to be giving an error. It's looking for the minimum, not the maximum. So we'll say, okay, well, cool. I want to find the highest point of the orbit. So I'm going to say, try and figure out the highest value that you can get from this function. And it should do that. It should say, okay, well, let me see. What is the altitude that we're at when the maneuver starts? And if I try a second later, what is the altitude then? And a second later, what is the altitude then? And until it can't improve it, it's going to keep walking in that direction. And because our altitude is going to increase and then decrease and not just randomly increase again, it's not going to be a bumpy graph. We don't have to worry about getting stuck in these kind of local areas where we go, oh no, I can't take a step in any direction that improves things, but I haven't found the best possible answer. Now, just because I know this is not going to work for our purposes, I'm going to go ahead and say local result. Well, yeah, that's fine. Local result is that, and I'm going to just say print result, and then we'll return the result. Okay, just so that we can take a look at it as it goes through this process. So now in theory, we've written everything that we need to write to make this work. I'm going to jump back up here, and I do have a crafting orbit, so I'm just going to comment out these things, and if I go to do transfer, I'm also just going to not execute it just yet. So we'll strip out the actual execution part. Oh, yep, and I'm missing a closing paren. Let's go ahead and fix that. All right, so we can see this is already starting, and it's evaluating this maneuver. And the problem is that we're using a hill climbing algorithm to slowly walk our maneuver around, and then to evaluate every individual maneuver, we're very slowly walking up the time. We're basically walking around the orbit, seeing if we're at apoapsis. And you see, it's not even moving this maneuver. It's printing out the scores that we're getting. It's slowly finding the highest altitude that we're going to get to. but man, it is taking forever to do it. So this is an algorithm that is simply too slow without us making some optimizations to really work. You see, we've already passed by the maneuver, the single maneuver that we're still in the process of evaluating. In theory, if we left this long enough, it should work. It'll eventually crawl its way along the orbit until it finds the highest thing, and it'll say, hey, I can't improve on that. That is what the error is for that maneuver. And then we'll say, cool, now let me look at a maneuver 1 second later and see what the Apoapsis is there. It's taking way too long. So we're gonna look at another strategy, and this is something that I started to talk about toward the end of the last episode. Didn't do a great job of explaining it. We're just gonna jump over and take a look at that right now. So what we're going to use is a ternary search algorithm. Now this is a technique in computer science for finding that you can read, finding the minimum or maximum of a unimodal function. Oh, that's helpful actually. This is a great chart that shows exactly the problem that we can sort of encounter, because if we're looking at the distance to the moon, well, we can get stuck in this local minimum or this local maximum, which is not the best option, but we also can't improve on it by making tiny little steps in any direction. So we get trapped in these peaks or in these valleys, depending on whether we're looking at the high values or the low values. But thankfully, we don't have to worry about that in the case of our altitude, because that is unimodal. Unimodal means that it's vaguely like this. It's not going to have two bumps. It's only going to have one bump. As long as we have one bump, then we can solve the problem. So I'll leave it to you whether or not you want to go through and read this, but the gist is, hey, we get a free algorithm that will solve this for us. And it's going to narrow down the range in which we're looking until we get to some precision that we care about. And then we can find our maximum altitude that way. So we're going to use this not to find the closest approach, but to find the point of maximum altitude. And then we'll just get the distance to the moon at that point and use that as our score for our maneuver. So I'm just going to copy this straight over, and we'll work with it. Okay, so distance to the moon at Apoapsis, and we're just going to paste this in, and I'm going to start making it into CheersKevin. So def ternary search, we don't use def, we use function. So it's function ternary search, and rather than putting parameters like that, we'll say parameter f left right absolute precision dot. We can dedent that. And this is already set up to find the maximum. We are happening to look for the maximum, which is great. Do I shift tab? There we go. Okay. Yeah, we got to convert this into proper CheersKevin, but that's easy enough for us to do. While true, we don't have while true, but we do have until false, so that'll work. So remove that line. And the idea is that, yeah, we have to just give it a function, a left bound and a right bound, so the area in which to search, and then say, how precise do you want us to get it? So until false, if the absolute value between right and left are within the threshold that we care about, then just return left plus right divided by 2. And in fact, this is already pretty much CheersKevin, which is great. I'll do that. We'll say local left third is right minus left over 3. Whoops. Oh, where did I go? There we go. Local right third is right minus left divided by 3. And I'm just going to add these spaces in here because I want my code to look beautiful. Little white space never hurt nobody. Okay. Then we have this condition. So basically what it's doing is it's picking these points on the graph and it's saying, it's doing comparisons between the right and the left and trying to shave off the left side or the right side because they're, just to try and find that maximum or minimum. If f with the left, f of the left third is less than f of the right third, well, then we can trim off the left part of our graph and just look at what remains. Otherwise, we can trim off the right part of our graph and look at what remains. So set right to right third, set left to left third. And I'm just going over this real quick to make sure there's nothing that jumps out at me as being particularly crazy. Ternary search parameter F, left, right, absolute precision. If we are close enough, if the distance between, so what we're doing is we're giving it we're going to be giving it some time to look at. I'm going to say, hey, find the biggest altitude in this time, left and right. This is basically the start time and the end time of where we wanted to search. And we'll say, hey, okay, find to within 1 second the time of Apoapsis, and then it will go ahead and do that. Oh, there we go. There's something that's gone wrong. I suspect that's the editor, and more than a. There we go. You can dedent that too. All right. So I think this is right. Let's see. Yep. And we're slowly we're changing left and right until we get them close enough. And that'll work. So now when we're trying to calculate Apoapsis time, instead of using improve converge at all, we're going to use our ternary search. So we need to figure out the arguments we're going to pass in. Ternary search. We're going to need to give it a function. I'm going to call it Apoapsis at. And do that because we're passing a reference to the function and not the result of calling the function itself. And where do we want to search between? Well, I want to search between when the maneuver starts, so time seconds plus maneuver ETA, and halfway through the orbit that the maneuver is going to create. So time seconds plus maneuver ETA plus maneuver orbit period divided by 2. And I'm actually going to put, don't need to, but I'm going to put parentheses around here just to make it a little cleaner. Of course, that's getting messy, so let's go ahead and make that a little tidier. Oh, you indented for me. Thank you. Just so we can see these arguments. And then the last thing is how precise we want it to be. I'll say, yeah, get to within 1 second, please. To within a second, find the point where Apoapsis at is going to give the highest value. Now we just have to write Apoapsis at. And this has to take in a time, and then it needs to give us back the altitude at that time. Or yeah, we're looking at Apoapsis at is probably misleading. Altitude time, altitude at. Altitude at parameter time, and then we'll just use the same thing that we did before. Copy that. We want to compare with Kerbin. Just say, cool. What is the magnitude of the difference in position between the ship and the center of Kerbin at that particular time? Except Apoapsis time is now t. Apoapsis time is now t. So this AA altitude, okay. This ternary search is a heck of a lot faster. It's operating on it's a O log n, which is fancy talk that doesn't necessarily matter. But we should be all set now. I am going to jump over into. Why is it highlighting that? Yeah, no, we're good. Do I have it? Do I have all my periods everywhere where they're supposed to be? Yes, I think I do. Let's jump over and give it a test. Unexpected token found. Oh, yep, I missed a end of instruction. I missed a period. Let's go and fix that up. And we are working. Let me jump out to the map real quick. You can see it is searching. And we can see, we at least now see that it's able to evaluate multiple maneuvers. It's not stuck trying to figure out, I mean, because we were taking forever just to find how good or bad a single maneuver was. Ooh. Why did we stop? Have we stopped? Oh, it says it ran. Okay. Aha! Okay. Oh, man, I was putting debug statements all over the case. I was going to get really frustrated because, man, I'm very excited to move past this. We don't have a return statement here. So when it's trying to optimize for whatever the return value of altitude at is, I mean, who knows what that... It's basically... yeah, okay. Oops. Yeah, I'll fix that up. Remove our print statements. Let me clean this back up. We just didn't have a return statement on the altitude at, so basically what it was getting back was 0. So it goes through this ternary search. It's finding 0. Is 0 less than blah? No, then you narrow in from the right side. Never had anything to actually optimize against. So get that return statement in there, and then things should be very fixed up. There we go. It's moving things out now. And it should, in theory, be at least finding better scores. We're at 100 meters a second at delta V, 200 meters a second at delta V that is trying. And it is, if we see, it is very clearly pushing its apoapsis, its predicted apoapsis, toward the moon. What it's really doing is it's trying to push the predicted apoapsis to where the moon is going to be. Once we get a transfer, then it's going to optimize the periapsis, because we're using both of those as kind of the resulting distance. And we're letting this thing just kind of walk itself up to the optimal orbit. And of course, it's got to shift around a little bit. There we go. And it's making its nudges. And there we go. It ran. We can see it got a periapsis so low that it's going to collide. And we've added this to our flight path. So I would run this, but we would collide into the moon. Next, we have to worry about, well, trying to slow down. But that'll be something we have to tackle in the next episode. Until then, I don't know. I'm very glad to have this transfer thing underway. It's been interesting because I've done this before in a previous series. What I did in the previous series was wrong, and it just so happened that we didn't run into the same issues. Or I mean, there were occasionally fiddly things, but this is a strategy that will work for us. And in almost all situations, because we're going to be doing these Hohmann transfers where really using the apoapsis as the point where we want the closest approach to be is a legitimate strategy. So now that we've got that all working, I appreciate you sticking with me, and in the next episode we'll tackle trying to slow down. So I hope to see you then. Cheers.